you all in the lecture of IC engine, fuels and lubricants. In this lecture, we will discuss about the thermodynamic actual cycles, because in last lectures we have discussed the air standard cycles, their efficiencies, mean effective pressures, evaluations. After that, we have discussed the fuel air cycle, where we have taken some assumptions like specific heat and dissociation of products gases at higher temperature, and rest was same as that of air standard cycle efficiency. Now, we will discuss the actual cycle efficiency. So, this is the content of today's lecture. We will discuss in this lecture the actual cycle, what are the actual cycle, what is the difference between real cycle and fuel air cycle, what are the criteria of their difference, and then we will discuss the testing and performance of SI or CI engine. So, actual cycle, we see from this slide that actual cycle is derived from air standard cycle. Air standard cycle is having the maximum output and maximum efficiency, and here in a air standard cycle we take specific heat, no dissociation, specific heat constant, and the working substance carrying no chemical changes in their composition during the cycle, and there is external heat source, external heat rejected, there is no source of ignition in that. The working substance was only the air. If we correct the air standard cycle for specific heat variation and dissociation, then it gives you the fuel air cycle. Then if we correct it for further losses like combustion losses, time losses, direct heat losses, exhaust blowdown and pumping losses, it give you actual cycle. So, what is the combustion losses? Because in assumptions of derivation of fuel air cycle, I have taken the combustion is instantaneous, which is not possible practically, because the crank travels during the combustion process. It is not possible that cranks remains at one position and combustion occurs. That is why here the combustion is taking place in a finite interval of time. There it was instantaneous as well as in fuel cycle as well as in air standard cycle. So, in these are the difference between real cycle and fuel air cycle. So, first is time loss. What is time loss? It is also called as burning time loss, and it includes the incomplete combustion also. So, this loss is due to the time required for making of fuel and air for combustion, means that combustion is taking place in some interval of time. Means you can see here that in Otto cycle, in ideal or fuel air cycle, combustion start from 2 to 3. So, when 2 to 3, this clearance volume remains same, means the piston remains at this position. This is piston, top dead center or inner dead center. So, it remains at this point. When the when it remains at this point, and the crank angle theta is constant until the whole combustion occurs, but it is not possible practically. This crank is moving continuously. So, the combustion is will be not taken at constant volume, it will be like this, it will have some movement. His volume is, the combustion process is not at constant volume, the crank is moving continuously, that is why this loss is called time loss. So, this loss is due to the time required for the making of fuel air of the combustion, because if we talk about SI engine, the in SI engine what happens in SI engine, fuel air mixture, already prepared fuel air mixture is sucked into the combustion chamber. So, that fuel air mixture is homogeneous in case of SI engine. If we take the case of diesel cycle, charge is not sucked, there only the air sucked, and after the compression, high compression of air at very high pressure, the fuel is injected over that air. So, that mixture or charge is formed within the cylinder. In SI engine, this charge is already formed. So, in diesel engine, the air fuel mixture is heterogeneous. This mixture is you can see here that this mixture is represented by a term called equivalence ratio. What is equivalence ratio? It is the ratio of fuel air actually used to the fuel air mixture theoretically or stoichiometrically or chemically correct used. So, the value of phi, if it is 1, then it is chemically correct, if less than 1 lean mixture, if greater than 1 for rich mixture. So, the value, this time loss, which is the burning time loss, depend upon the value of air fuel mixture equivalence ratio. Either that air fuel mixture here is lean, means having the value phi less than 1, or it is chemically correct, means having the value of phi equal to 1, or it is rich, means having the value of phi greater than 1. So, it depend on that. Other than this, it also depend upon the geometry of the combustion chamber, size and geometry of the combustion chamber, because in SI engine what happens, we create a spark. So, a spark is created and this spark is propagated throughout the mixture. So, that is called flame velocity. So, how the flame is traveling, if the flame velocity is very high, the time loss will be less. If the flame velocity is very low, the time loss will be higher. So, it depends also on the type of fuel used, quality of the fuel used. You are using high octane fuel or low octane fuel, or high cetane fuel, cetane number fuel, or low cetane number, cetane and octane number, these are the value for good SI and good diesel engine fuels. So, fuel characteristics also play a very important role for deciding the time loss. So, this loss is due to the time required to mixing of fuel and air for the combustion. So, it is very major in case of diesel cycle as compared to petrol engine because in diesel cycle the mixture has to be formed, the fuel air mixture has to be formed. So, time loss plays very important role in that diesel cycle, very high. Now, the second difference is first we discuss that totally the time loss. So, time loss also include the incomplete combustion loss. What is incomplete combustion? Means it also depends upon the quality of the fuel. If the quality of fuel is not so good, there will be incomplete combustion means if in the products of combustion carbon monoxide and carbon dioxide exist, it is known as incomplete combustion, and it is practically always the incomplete combustion. There is no possibility in the engine that it will be 100% combustion, it will be incomplete combustion. So, the time loss depend upon the spark advance and retard affects the time loss. So, I will discuss you later. First we discuss these what are the losses which we consider in actual cycle, which was not considered in the fuel air cycle. So, first was time loss. which is defined as this. Now, the direct heat loss, what is direct heat loss? In air standard cycle, we have considered that there is no interaction between the gas and the cylinder wall, which is not possible practically. Here we will consider that, because there is heat loss from the piston head, from the cylinder walls, as well as from the cooling water jackets, heat is lost, some radiation losses are also there. So, if we consider these heat losses, then the actual cycle will be formed. So, in direct heat loss, this is due to the flow of heat from gases to the cylinder walls. Exhaust blowdown losses. What is exhaust blowdown? I will discuss you in the coming slide in detail. In short, we can see here the loss of work on the expansion stroke due to early opening of the exhaust valve. In that valve timing diagram, we have discussed the valve timing diagram for ideal cycle and actual cycle. So, in that we have seen that the exhaust valve was not open at the bottom dead center. It was opened 30 to 40 degree before to the bottom dead center. So, because of that opening of the valve, earlier opening of the valve during the expansion stroke, it occurs in losses, because in expansion suddenly if you open the valve, the pressure goes down. So, this is because of that the blowdown means pressure difference, suddenly the pressure difference, because if you open the valve, suppose during the expansion, at the starting of the expansion, let the pressure is about 80 bar, and at the end of expansion ideally I have assumed that pressure is 1 bar, which is atmospheric. But if you open the valve at 7 bar, for example, I am open the valve 7 bar. So, 7 bar and 1 bar atmospheric pressure, it gives you the pressure difference. Because of that, losses are there, that is called pressure losses. Pumping losses, in all the cycles I have considered only the compression, then heat addition, then expansion, then heat rejection, but I have not seen you the this suction and expel of the products. So, pumping loss are because of that. So, pumping loss is due to the pumping of gas from low inlet pressure to high exhaust pressure. I will see you in the later slide through the diagram. Rubbing friction losses, you know that the reciprocating engine, there are relative motion between different components in cylinder, piston, some bearings, auxiliary bearings are there. So, they are there because of that some work is lost, energy is lost. So, if we consider this rubbing friction loss, we will approach toward the actual cycle analysis. Now, come to the time loss. I have already discussed about the time losses, also called burning time losses. So, time losses include in complete combustion also. So, spark advance and retard affect the time loss. What is spark advance? Spark advance means here if we create a spark at top dead center, then it is at top dead center. If we create a spark here, then it is spark advance, and if we create a spark after that, then it is called spark retard. So, the spark advance and retard affects the time loss. Suppose here you can see here that here the spark in ideally we create here spark, but in actual condition spark is created here. Why we create a spark here? Because flame takes some time to travel to the combustion chamber. So, it needs some time for combustion. So, we create a spark here, not at the top dead center. So, because of that suddenly what happens, because of spark pressure will be rises like this, and because of the continuous movement of the crank, it will be the heat addition process will be like this. So, this much amount of loss occurs, this is time loss, So, I have already told you that flame speed depend upon the type of mixture, equivalence ratio. So, for rich mixture it is low, and thereby increasing the time losses and lowering the efficiency. These are some diagram for time losses. Spark at top dead, if we create a spark at top dead center, then 1 to 2, if we create a spark here, then it will the pressure rise will follow this route. So, this much amount of loss is there, this much amount of loss is there, this is because of time loss. That is why we never create a spark at the top dead center, we retard the spark. So, combustion here you also see that we are creating spark at 39 degree before, means before top dead center 39 degree before top dead center I have created spark here. So, this much amount loss was there, and if we optimum this spark, because for different size or different RPM and different types of engine, this spark timing is optimum. So, for we can optimize this at once and we can go for minimum time loss, because it is not desirable. The effect of time loss is decrease in the work output. Now, difference between the real cycle and fuel air cycle on the basis of exhaust blow down and percentage of losses. So, first discuss this slide. So, what is percentage of losses? From here you can see that the time, because of time losses, the efficiency reduces by 6%. It is experimental analysis. 6% of the efficiency is reduced because of the time losses, and because of heat losses 12% of efficiency is reduced. So, this was some analysis of fuel air cycle and real cycle. So, the fuel air cycle is having 18 to 20%, the real cycle is having 18 to 20% less efficiency, thermal efficiency as compared to fuel air cycle, because here I have consider various losses, time losses, heat losses, rubbing friction, exhaust blow down, etc., pumping losses. Now, come to the what is exhaust blow down loss. So, exhaust blow down loss, it is expansion process, it is similar that it is for Otto cycle, let it somewhere here. So, expansion start from here. So, I have discussed it that at very high pressure expansion occur, and here the top dead, this is the your extreme end and this is the top end, top dead center and bottom dead center. So, here at the bottom dead center, if we open the valve at bottom dead center, the diagram will be like this. But we open the valve before bottom dead center to give time, so that the amount collected, combustion product collected can be gone out into the surrounding. So, we open, if we open early exhaust valve, if we open early here, this will be followed like this. So, this much the loss, this loss is called exhaust blow down loss, because this represent the loss in the PV area in the PV diagram. It is, so that is why it is the loss. So, early exhaust valve open gives you this much amount of loss. So, exhaust valve opening at the bottom dead center, if we open the bottom dead center here, let you are opening exhaust valve here. So, it will be like this. So, this much amount of loss will be there, this much amount. So, we always optimize the opening of the exhaust valve, and how you optimize it, it depends upon the type of the engine, high speed, low speed, or which type of engine is this, which type of fuel will be to be used. So, it depend on that. So, it is always optimized. So, where it has to be open. So, if you open it at some pressure, let if the cycle pressure is 3.5 bar here, then this loss will be somewhat lesser, this diagram will be lesser, this area will be lesser. If we open optimum exhaust valve opening at 3.5 bar, if we open it at 7 bar, there will be this loss. If we open it at atmospheric pressure, then this will be the loss, and if we optimize it at some pressure, let it is 3.5, the loss will be lesser. So, it is not a thumb rule that it should be 3.5 bar. It depends upon the size and type of the engine and which fuel it will be used. Now, come to the pumping loss. You can see from here it is PV diagram. So, here this is the actual PV diagram. So, here actual PV diagram, why it is actual? Because here all is happening actually, it is the heat addition is not at constant volume. Here this shows the suction which is below atmospheric, this is atmospheric line. So, here it is suction process, then after suction compression will be start, and at this point somewhere let at this point ignition is given through the spark plug, because this is Otto cycle, actual Otto cycle, it is actual PV diagram of a SI engine. So, if you give spark here, so it will not be at constant volume, it will be like this, then expansion, and let at this point you open the valve. So, here will be a curve, and the working substance will come out at above atmospheric pressure, and again the piston suck the air. So, it includes suction and exhaust stroke both. So, this is positive diagram, this is positive indicator diagram, which gives you the work given, net work output. So, net work output from this actual cycle is equal to, let this area is A1. So, A1, and let this area is called pumping loss, because there is pressure difference, there is always a pressure difference between intake and exhaust stroke. So, because of that a loop is formed, that loop area, let its area is A2. So, if we subtract this A2, it will give you the net work output. So, the pumping loss, the difference of work done in expelling the exhaust gases and the work done by the fresh charge during the suction stroke is called pumping work. It is due to the pumping gas from low inlet pressure to higher exhaust pressure. This loss increases at part throttle, because throttling reduces the suction pressure. Throttling means in SI engine we use some throttle valve for increasing or decreasing the fuel supply. So, if we apply the throttle, because of throttle suction, it reduces the suction pressure. So, this loop area is increased, and it also increases with the speed of the engine RPM, and this is the rubbing friction loss. The piston friction increases rapidly with the engine. We all know that from the relations, we know that the piston friction is dependent upon the engine RPM, and it also increases with the mean effective pressure. Mean effective pressure means the pressure of the cycle. What is mean effective pressure? Mean effective pressure is this mean effective pressure is equal to net work, which is evaluated from here, upon, let this is V1 minus V2, then let this point is 1, 2, 3, 4. So, upon V1 minus V2. So, these were some difference criteria for actual cycle and air standard cycle and fuel air cycle. Now, we are going to start the testing and performance. So, we have already discussed these testing and performance in lecture 1, and what are the parameters for this to measure? We measure the indicated power, which is the fuel energy used to push the piston. We measure the brake power of the engine 2 pi Nt by 60, friction power is the ratio, it is the difference between indicator power and brake power. We measure mechanical efficiency, which is the ratio of brake power or indicated power, volumetric efficiency, it is the breathing ability of the engine, because the power developed by the engine is a function of many parameters, its fuel air ratio, volumetric efficiency, the calorific value of the fuel used, etc. Engine RPM, there are number of variables on which this power, actual power developed by the IC engine depends. So, we have to evaluate these parameters to declare the value of power output or efficiency of the engine. So, the indicated efficiency we have already discussed it, indicated power upon MF into CV, brake thermal efficiency, brake power upon MF into CV. Indicated specific fuel consumption is the fuel consumed per unit power developed. Similarly, brake specific fuel consumption is fuel consumed per unit brake power developed. Mean effective area, it is formulated as net area of the indicator diagram is the PV representation, PV pressure volume variation. So, net area, which was I have shown you, that is A1 minus A2 upon length of indicator diagram, it is given for the instrument, and spring constant is also given for the instrument. So, experimentally you can evaluate MEP, and theoretically it is net work upon V1 minus V2 swept volume, and I have also discussed the equivalence ratio. So, the equivalence ratio is the actual fuel air upon stoichiometric fuel air. So, there is no instruments with the help of that you cannot measure directly, there is no instrument that you can measure the fuel air ratio directly or brake power directly. So, these are the some measurements which we do before evaluating these parameters. So, we will measure the RPM of the engine, fuel consumption is measured with the help of some stopwatch and burette method, and air consumption is also measured with the help of orifice meter. Brake power is measured with the help of some dynamometer. There are different types of dynamometer which is not in your course. So, it is measured from the dynamometer. Indicated power is from indicator diagram, friction power, heat carried away by cooling water, it is evaluated, because the cooling we need cooling of the engine is needed because of some metallurgical point of view, it is needed. And that exhaust gas analysis, we exhaust heat gas, because the many high amount of heat is carried away into the surrounding with the exhaust gases, and exhaust gas analysis of CO, CO2, NOx, oxides, sulfur dioxide, these are the analysis in exhaust gas analysis. And smoke density means opacity of the fumes formed. So, this was all about for today's lecture. In this lecture, I have told you about the difference between the actual cycle and the air standard cycle, and we have also discussed about the factors on which it depends. Thank you so much.